primary goal today is the relationship between displacement, velocity, and acceleration. At this point, with example 2, we're going to derive those height of a falling object equations that somebody told you in higher algebra that was what you used in order to find the height of a thrown or a falling object. So we talked a few moments ago about the fact that if you drop two things, they're going to fall and hit the ground at approximately the same time because they're both subject to the Earth's gravitational pull and acceleration due to gravity. I hope you all have seen this before, but acceleration due to gravity, assuming that you're standing on the Earth, is negative 32 and it's constant. Okay? Okay, taking that for granted. If you move away from Earth, it gets weird because it's not the same. Okay? Acceleration is negative 32 feet per second squared. Now, if we have acceleration, how do we get to velocity? We did the derivative relationship the other way a couple of months ago. If I have acceleration, how do I get to velocity? Some of you are whispering, and you're right. You're going to anti-differentiate with respect to time. Okay? Technically, this is velocity plus a constant on the left. And on the right, what's the antiderivative of negative 32 with respect to time? Constant becomes what? Becomes linear plus some sort of constant of acceleration, or some constant of integration, right? Okay. Now, I would make the argument that you don't need both of these constants. Like, mathematically, going from here to here, you need a constant on both sides. But I could take this constant and move it over here, and it would still just be a constant, right? Okay, so I'm going to say that v of t is equal to negative 32t plus some sort of constant. Okay. Then how do I get from velocity to displacement? Integrate again. So to get to displacement, I do an antiderivative again. I'll go up over here now. Antiderivative of velocity is s of t plus some sort of constant. The integral of negative 32t, we're going to use power rule on it. It's going to be negative 16t squared plus that constant we found originally times t, and then we've got another constant on here somewhere as well. Okay? So one could make the argument, for the same reason we just did, negative 16t squared plus some constant times t plus some other constant of integration. Okay? How are we doing? What do we typically use in place of that c? Remember what term goes there? Typically refer to that as initial velocity, wouldn't we? And what do we use for this one? Say it louder. Initial height, which leads us to negative 16 t squared plus v naught t plus h naught. Okay, that is on Earth in feet, the height of an object if you throw it or if you drop it. Okay. Now, these get challenging. Don't close down on me now, because these get challenging when we move away from Earth. Can you imagine going somewhere other way from Earth? Good? Wouldn't that be awesome to go somewhere away from Earth? Nobody wants to head to Mars with me? I'm in. I'm going. Going to Mars. How about tomorrow? Can we go to Mars tomorrow? Nobody's coming. All right. Things get weird when acceleration is not constant. The acceleration now is a function that is not constant. This gets weird. And we still have to use that process of anti-differentiating. Now, we didn't use any initial conditions in the last example, and I'm going to show you how to use them in this example. So if I start with acceleration, the first question is, or it says what's the position and velocity if it's two given initial conditions. Let's distinguish between these two initial conditions. 0, comma 40, is it giving me a position, a velocity, or an acceleration? Position. 60 feet per second, is it giving me a position, a velocity, or an acceleration? Keyword, the key phrase there is the units. Feet per second, it's giving us a velocity. Okay, so here's what I'm going to do. I'm going to integrate acceleration, and I'm going to find the constant of integration. I'm going to integrate velocity and find the constant of integration for the next one using the initial condition. So, if I have A of t, how do I get to V of t? Integrate with respect to time. Integrate with respect to time. Okay. I'm only going to use one constant of integration, but you see why there could be two, right? This is going to be V of t on the left. What's the antiderivative of e to the negative t? Don't you love e to this? Is that the correct antiderivative? What else do I need? I need to divide by that -1. So negative e to the negative t plus some constant of integration. Do we know the value of that constant of integration? Be careful. Popular wrong answer for the value of c. You ready for the popular wrong answer? 60. Wait, Mr. Best, 60 looks right, doesn't it? You tempted to put 60 there for the constant of integration? Not at all. Good for you. 60's tempting, isn't it? Can I show you why 60's tempting for the initial velocity? Initial velocity tells us that t equals 0. So I'm going to go with v of 0 is equal to negative e times negative, or e to the negative 0, plus some constant of constant of integration. And what is this initial velocity equal to? 60. Is c equal to 60? It's almost 60, isn't it? If acceleration was constant, wouldn't it be 60? But acceleration's not constant. What's e to the 0? 1. 1 plus c is 60. So c is, no, that's, sorry, negative 1 plus c. So c is 61. Okay? Now, this isn't giving us a new initial velocity. It's just saying because the acceleration changes, we're not necessarily going to have an initial, or we're not going to have a c value of 60, even though that's our initial velocity. So, velocity is what? V of t is negative e to the negative t plus 61. There's our velocity equation. Questions so far? Okay. We have velocity. Let's go to position. How do we do it? Integrate again. Integral of v of t dt, integral negative e to the negative t plus 61. I'm going to integrate the velocity function. That's going to give me s of t plus some constant, but I'll ignore that for now and put it on the other side. Antiderivative of negative e to the negative t. E to the negative t. We get rid of the negative again. Plus, what's the antiderivative of 61? 61t plus a constant of integration. Okay. How do I find this c value? Plug what back in? We were given the 0. It was 0, comma 40, right? Does that look right? I can slide back up and show it to you. S of 0 is equal to e to the 0 plus 61 times 0 plus c, and I was told that that was 40. That part's gone because it's 61 times 0, but this part's 1. And that is our position equation. Okay? Another good example here where they give you this. These are all of what we're doing today is objects in motion. You're not always going to start with acceleration. This one starts with velocity. It gives us a velocity function, and it's going to ask us to use what we already know to talk about the motion of the particle, and then also to talk about the position of the particle. So keywords here, we want to know when it's moving right, moving left, and stopped. If you go back to the first page of your notes, we didn't highlight it together, but I hope you have an idea for what's true about velocity when it's moving right, moving left, and when it's stopped. Okay? I have a tendency to start with this one because it's a lot easier for me, especially when the function gets complicated. It's a lot easier for me to tell when the object is stopped than when the object is moving in a particular direction. And if I know it's stopped, it's got a chance of changing direction. I'll show you what I mean. Okay? So I'm going to go with stop first. What do we know about velocity if the object is stopped? Velocity is equal to 0. So I'm going to go ahead and say t over 1 plus t squared equals 0. What t value or values does that happen for? T equals 0 is the only one. Okay? Convince yourself. Take another 20 seconds, just in your own mind, to convince yourself there's no other t values that make the object stop. Okay, we good? -1's kind of tempting, isn't it? A little tempting, but you need to convince yourself algebraically or arithmetically that -1 doesn't make the object stop. Okay? So now, if we know when it's stopped, and this is the only place it's stopped, this is the only place it could change direction, right? Also, because if I look at this denominator, there's no place where that denominator is ever going to be 0, is it? Because I got a squared there and a +1, so the denominator will never be 0. I've got no singular points. I've got a stationary point, but I've got no singular points. Singular points being where the derivative is undefined. Okay? So this is the only candidate for a place the object could change direction. So what I'm going to do is this. I'm going to do a v of t number line and do a test interval. I know that it's stopped at 0. I'm going to check the velocity to the right. I'm going to pick an easy one. I'm going to check the velocity to the left. Okay. And we'll talk about it. You don't need to do all of this right now, but I'm going to do all of it and then explain why I didn't need to do some of it. Okay. Let's do the positive first. What's v of 1? Moving right or moving left? It's moving right. Why? Okay, it's moving right for t. I need to put an h in my right. For t greater than 0, because velocity is greater than 0 on that interval, right? Are you convinced that its velocity is positive for everything greater than 0 on the time continuum? Why can't the velocity ever go negative over here? Because what would need to happen if the velocity were to go negative on that interval? You'd need a 0 again, wouldn't you? Will the velocity ever be 0 again? No. So it's strictly increasing for that entire interval. Okay. What about v of -1? I've got -1 over 1 plus 1. That's -1/2. So the velocity is less than 0. So this would be moving to the left. How do I need to refine my response? This is the correct way of doing the work. How do I need to refine my response for this particular instance? What information did I ignore that I should be keeping track of? Right here. That's important information. Okay? So I need to keep track of that in the sense that I'm going to refine my answer for moving to the right. When is it moving to the right? It's moving to the right on that interval. When is it moving to the left? It's not. Okay with that so far? This is where we get to the good stuff. you have your calculators handy? Will you get your calculators handy if you don't? Okay. First, there's two questions here, and they're both really important. Find the particle's displacement for the given time interval. That's part A. And part B is if S of 0 is 3, what is the particle's final position? That's question B. These are two, and this is the last thing I'm going to do today, but these are two really important questions. Okay, first of all, how do I find displacement over a given time interval? Did this earlier today. I know velocity. What do I do to velocity to get displacement? Integral. I'm going to integrate over the time interval the function given. Will you punch that into your calculator? And once you've done that and got a numerical value, show it to a neighbor so you can convince each other you got the same thing. Is that what you got? 1.151. What are we in? Meters? 1.151 meters. What does that mean? Should I give it to you? This is the particle's change in position, over the first 3 seconds of motion that we tracked. Okay? Now, here's where it gets good. Let's look at question B. What's your answer for what is the particle's final position? Will you write it down and show your neighbor, show your friend? Is that what you wrote down? How many people wrote that down? Just quick show of hands. Write that down. Okay. Why 4.151? Because over the first 3 seconds of motion, the object gained 1.151 meters, but it was already 3 meters from wherever we're tracking its motion from. Okay. This is kind of a not backwards, but it's kind of a roundabout way of doing the fundamental theorem of calculus. This right here is displacement, right? With me on this? We all agree that this integral represents the displacement over the first 3 seconds of the object? Good. The fundamental theorem of calculus version 1 says if I have a function and I want to integrate it from A to B, what do I have to do? You saw it in this context. What do you first have to do? Find a what? Find n related to f. What do I want to find first? Capital F. Okay. Give me an antiderivative for velocity. For v. S, position, right? So is this? That's a legitimate equation for the displacement, right? Which also makes kind of sense. If I take the displacement at 3 and subtract the displacement at 0, I should find the displacement over a time interval, shouldn't I? Which now is an algebraic step away. This is what I want, right? If I add s sub 0 to both sides, this is another way of doing the fundamental theorem of calculus. To get a final position, you take a starting position and then add the displacement over the time interval. Okay? Those are the highlights from today. What I would like you to do for homework tonight, don't worry about the book work at this point. What I'd like you to do is I'd like you to do example 5 and example 6 on the back of your notes. And I would also like you to do as much as you can on the FRQs front and back that I gave you as you walked in.